Hi, everyone. We're back. We're going to continue talking about measurements in this segment. And so in the first segment, we talked about numbers, the number part of measurements. And today what I wanted to do, or in this unit, I wanted to talk about the unit part. And so before we start, what I really wanted to talk about, so if you're keeping notes, we're now on the units part. What I wanted to tell you about is base measurements. Out of all the things in the world or in science that you can measure, there are 7 base measurements that can be made. They include mass, and mass we're going to define as a measure of inertia in a future chapter. We're going to have length. Some people call that one distance. Time is a base measurement. Temperature is a base measurement. Amount of substance, which we're going to hit in a later chapter, not for a while. And then the last 2, we really won't use in this class, but just for completion's sake. Electric current is another base measurement, as well as light intensity. So out of these 7 things, there are standard units. The units that are standard are put together by what's called a UPAC. A UPAC stands for the International Union of Pure and Applied Chemistry. And so if you were to publish a scientific paper, you would make sure all your units were UPAC units. They're the official units that are to be made. And those units would be, for mass, it would be kilograms. For length, it's a meter. For time, it's always seconds. For temperature, it's in Kelvin. Now, if you don't know what Kelvin is, we're going to get to that, so just hold on. Amount of substance is always in moles. Electric current is always in amperes, and light intensity is in candelas. Candelas are abbreviated CD. By the way, I wrote out the whole word, but mole is abbreviated MOL. So those 7 base measurements are the core of all other measurements. And so, and you might see other units besides for these standard ones. And one thing that you might see is the metric prefix has changed, which we're going to come back to in just a moment. So these are the 7 base measurements. The ones we're going to use in this class are the first 5: mass, length, time, temperature, and amount of substance. We'll define mass in an upcoming chapter. We'll define temperature and amount of substance. And I believe everybody knows what length and time is. So those are the 7 base measurements, and all other measurements are called derived measurements, which means that you can get them from combining those 7 base measurements. 2 very common derived measurements would be volume and density in chemistry. There are hundreds, thousands of other derived measurements. Volume is the amount of space that something occupies. And you might remember from high school geometry classes, if you had a box. Oh, I didn't draw that well, did I? If you had a box and you wanted to, let me fix that. If you had a box, oops, my eraser's still on. There we go. If you had a box that looked like this, and I asked you to find the volume of that box, what would you do to find the volume? Well, you would take the volume to be the length times the width times the height. That's pretty standard that you would do. And notice that this length is a length or distance, width is a distance, height is a distance. And so volume would be a combination of those, combining 3 different length measurements. And notice the units would be, if this one was in meters and this one was in meters, if they were all in meters, if you had a meter times a meter times a meter, it works just like numbers. That would get you to a meter cubed. So volume is a derived measurement. Density is also a derived measurement. Density is defined as mass per unit volume. We're going to come back to this later in the chapter. But density is equal to mass divided by volume. and mass is a base unit, and volume is already a derived measurement. And so density is also a derived measurement. And its units would be kilogram for mass, meter cubed for volume. Although, of course, you might see other units than that, but it would always be units of mass over units of volume. So we're going to talk about the different units right now. There are others, just to give you some other ideas of force is a derived measurement. Force is equal to mass times acceleration. If you've ever had acceleration, I spelled that wrong. Acceleration. And so mass, again, is a base measurement, and acceleration is how fast it takes something to get moving. And so it's going to be time over distance squared. And so it's always a combination of those 7 base units or base measurements when you break down any other measurement that you could take. So the other thing I wanted to talk about are the metric prefixes. Now, since this course is online, it's a little bit challenging to make you memorize the prefixes and test you on that. The more familiar you are with the metric prefixes, by far the better off you are in the long run. There's no doubt about it. So I know for now you're probably going to be looking them up, but ultimately you really want to aim to knowing at least the most common ones like centi and kilo, milli, and micro. So I gave you a handout there's a handout, I'll show it to you. Oops, maybe I won't show it to you. Here it is. Here is the metric prefixes, and those are taken right out of the textbook. So for right now, we're going to stick with the most common ones, but ultimately, knowing the common ones will be helpful. And again, those are going to be kilo, deci, centi, milli, and micro. Those are the most common you're going to run into throughout the semester. So you might want to refer to that chart or print it out or keep it open on your screen as we talk about metric prefixes so that you have that. All right, so how do the metric prefixes work? They will change the order of magnitude of a measurement, or I should say of a unit, by powers of 10. So it's either going to multiply by powers of 10 or divide by powers of 10. And so, for example, if we had 1 kilometer, kilo stands for 10 to the third or 1,000 as a multiplier. So what you could say is that 1 kilometer is equal to 1,000 meters, and you would be replacing the K with the number 1,000, right? Because a kilo means times 1,000. Or you could have written that 1 kilometer is equal to 10 to the third meters. And again, it's the same thing. I'm replacing that K with its meaning 10 to the third. It's going to be important for you to know these relationships as we move forward. So another one example would be if I had 1 centiliter, right? You need to know that C stands for centi. And again, you can use that chart for now. And that centi means 10 to the minus 2, or it's a multiplier of 0.01. And so I could write 1 centiliter is equal to 10 to the minus 2 liters. Notice what I'm doing. The C is being replaced by its meaning. I myself like to use the exponents, so that's what you'll see me do throughout most of the lecture. Or you could also have written that 1 centiliter is equal to 0.01 liters. And if you notice again, I'm just replacing that C with its meaning. Oh, my decimal kind of disappeared. So you might also see some people don't like negative exponents, or they don't like this partial thing. And so sometimes you'll see it written in the reverse way. Don't let that confuse you if it's the reverse of this. And so what they would do is, instead of having the replacing the C, which is what I personally think is the easiest way to do, you might see that 1 liter is equal to 100 centiliters. And what they're ultimately doing there is taking the opposite of the meaning times this. So if I know that centi means 0.01 and I multiply that by 100, I get to 1, right? So what happens then is, if I have centi times the meaning, right, 100, I'm going to end up with 1, which would make sense, because then 1 liter equals 1 liter. So some people switch and sometimes use this method and sometimes use that method. And so I think whatever method you pick, you should stick with it, because the most common thing that people do is screw that up, and they end up writing down incorrectly that 100 liters equals 1 centiliter, right? That is not correct. So you'll get practice as we go through the problems with doing this. But again, I really prefer the exponents, and so you'll see me using the exponents. So let's just try another one to see how you do. 13.2 megagrams is equal to how many grams? So you need to know that M stands for mega, and that mega stands for 10 to the 6th, or a million. So if I wanted to do this, I'm going to replace the M, and I'm going to write it out as 13.2 times 10 to the 6 grams. And so this mega is being replaced by 10 to the 6th. And so you can practice a few of these, but you'll see as we're going through some more problems that this is a fairly common thing that we're going to need to do. Okay, so what else do I need to tell you about with these units? The fourth part is going to be unit conversions, which is kind of what we already started a little bit in the metric system, although that's a little bit easier. I really like to not just call this unit conversions, but you can use what's called dimensional analysis. And in dimensional analysis, what you're really doing is looking at the units to figure out what you have to do. If you get very, very good at dimensional analysis, it helps you to not need to know formal equations, especially when you get into physics. If you just look at the units, you can figure out, do I need to multiply these numbers, divide these numbers, add them? What do I need to do? But for right now, we're just going to use dimensional analysis to convert units. The basics of dimensional analysis is that you can take anything and multiply it by 1. Anything multiplied by 1 equals itself, right? If you multiply something by 1, you don't change it. And so to start out with, the other piece that I need you to know is that you're going to need to know what I refer to as equivalent statements. Now, again, since we're online, you can always look these up, but if we were in the classroom, the equivalent statements within the metric system, you're responsible for. And if you're within different systems, between systems, or within other systems, they'll be supplied. So what do I mean by other systems? Well, there's the English system, the apothecary system. There's a whole bunch of other systems of units. For example, we know that 12 inches is 1 foot, right? That's not part of the metric system. That's part of the English system of units. So within the metric system, you're going to need to know how to convert, because the difference is only given by the prefixes. If it's within the metric to English, or within the English and it's a unit you're unfamiliar with, those things you would have to really know a lot of. So they'll be supplied to you all the time. The other thing I wanted to point out about these equivalent statements is that some are defined and some are not defined. If they're defined, if you watch the significant figure video first, if they're defined, that means that they have an infinite number of significant figures. And we're going to practice this throughout all of the problems, and we're going to do it in the group meetings as well. So defined are always within a system. So when I say that 12 inches is 1 foot, that's exactly right. I could say 12.0000 is equal to 1.0000 foot. There's no end to the number of zeros I would have in that inches. It's an infinite number. Within the metric system, if I say 1 kilometer is equal to 1,000 meters, there's an infinite number. This is not one significant figure, and this is not one significant figure. There's an infinite number of significant figures. So don't use those defined ones to limit. However, if you're within systems, and I just tell you 1 inch is equal to 2.5 centimeters, this is different systems, is not defined. And if it is not defined, you have to use the sig figs given. Obviously the 1 you're not going to because it's meaning 1.000, but the 2.5 would limit you to 2 sig figs. Because it's not exactly that, it's actually exactly 2.54 centimeters, and that would have 000 after it. But if you're only told 2.5, you're only given 2 digits, you can only use 2 digits from that point out. Again, I don't want to get bogged down in the details before we start doing problems, but we'll practice these rules as we go through a bunch of different problems. So let's try some unit conversion problems and see how you do. Again, you're going to have more practice than this. This is just introducing the ideas. So let's try some practice problems. Let's start off nice and slow. 15 yards equals how many feet? You need to know an equivalent statement. Our equivalent statement is 1 yard equals 3 feet. This is defined because it's within the same system, so the sig figs aren't going to be a problem here. Now, how are we going to do this? Well, this is my equivalent statement. And what I'm going to do is take my equivalent statement and I'm going to turn it into a conversion factor. Now, a conversion factor is simply a fraction equal to 1 or equivalent to 1. So I could say 1 yard over 3 feet equals 1. This is now a conversion factor. Or I could have said 3 feet over 1 yard. Even though they don't look exactly the same, they mean the same. And so that's equal to 1. That's the same as if I would have said 3 over 3 is equal to 1. Or I could have said 6 over 2 over 3 is equal to 1. Even though 6 over 2 doesn't exactly look like 3, you know that 6 over 2 is equal to 3. And so as long as your numerator is the same as your denominator, it's equal to 1. So when you have an equivalent statement, you're saying that the 1 yard is equal or the same as 3 feet. And so you can make a fraction out of that that's equal to 1. Now, which conversion factor do you need to use to solve our problem? Well, if I start out with 15 yards, I'm going to take that and I'm going to multiply it by my conversion factor. Remember, my conversion factor is equal to 1, and I can multiply anything by 1 and not change it. So now, which one would I want to use? I want to end up having yards go away. So if I have yards on the top, you could pretend if you want that that's over 1. I'm going to need to put the conversion factor 3 feet over 1 yard because I want yards to cancel. And now what am I going to have? 15 times 3 is going to be 45, and the unit I have left will be foot. So what if it was the reverse way? What if I asked you 15 feet equals how many yards? I would still be using the same equivalent statement. I would still be using this equivalent statement, but now I'm going to have to use it in a different version. So now I would start with my given. This is my given in the problem. 15 feet, and I'm going to multiply that by a conversion factor. right? This is going to be my conversion factor. And now I want to get rid of feet. So I'm going to put 3 feet on the bottom and 1 yard on the top so that feet cancels. And now I'm going to have 15 divided by 3. 15 divided by 3 is 5. I'm going to say yards. So technically, if I was doing this, 15 is 2 sig figs, so I would need to say 5.0, but we'll come back to that and be more harsh as we're moving along. So this is the very basic type of problem that you would do for any kind of conversion. So let's try another one. What if I asked you 4.5 centimeters equals how many inches? You need an equivalent statement. The equivalent statement is that 1 inch equals 2.54 centimeters. So this is my equivalent statement. If you don't have this, you can't solve the problem. So this is my given. I'm going to take my given, 4.5, and I'm going to multiply it by a conversion factor. My conversion factor is going to be, again, a fraction equal to 1. Oh, I forgot to put my unit on there. So let's, 4.5 centimeters times my conversion factor. Now I want to get rid of centimeters in this problem, and so if this is already on top, I need to put centimeters here. So I'm going to have 2.54 centimeters, 1 inch here. I'm going to have to take 4.5 and divide it by 2.54. If I do that on my calculator, I'm going to get 1.7716 and maybe a couple more numbers. Centimeters will cancel. I'm now in inches. Now I don't want to give all of those numbers. 4.5 is only 2 significant figures. This is 2 significant figures. So I want to give my answer to 2 significant figures. Now notice if I have this 1.7716, I want to keep the 1, I want to keep the 7, I'm going to get rid of that 7, so I'm going to need to round up. Because the number I'm dropping is 5 or greater. So my answer that I'm going to give is 1.8 inches. What if we made it a little bit harder? And what if I said 4.5 centimeters squared is equal to how many inches squared? Now this one's a little bit trickier. So in this case, I'm still going to use my 1 inch equals 2.54 centimeters. However, if I start out with my given 4.5 centimeters and I multiply it by my conversion factor and I say 4.5 centimeters squared, I say 1 inch is 2.54 centimeters, and that's all I do, I'm not going to be okay. That's because 4.5 centimeters squared is like 4.5 centimeter times centimeter. And if I take that and I go 1 inch over 2.54 centimeters, and I only do that, that centimeter will cancel with one of them. But if I stopped right there, my unit would be centimeter times inch. I don't want that. So what I need to do is multiply it again. So that both centimeters cancel. And now I'd end up with inch times inch. And now mathematically, I'm going to say 4.5 divided by 2.54 divided by 2.54. Now be very careful on your calculator. You need to make sure that both of the divisions are going on the bottom. So your calculator just goes by order of operations. So right now I think that it will be okay, but as we get to future problems, I'll show you some places where that might go astray on you. If you punch that into your calculator properly, I think you're going to get this number, maybe some more digits. Again, 4.5. We're looking at 2 sig figs. And so over here, I want the beginning 0, not significant. And keep the 6, we're going to keep the 9, we're going to drop a 7. So I have to round up. Now I'm going to round the 9 to 10, which means if that goes to a 0, the 6 has to go to a 7, so properly rounded. That's going to be 0.70 inches squared. Or if you go to scientific notation, it'll be 7.0 times 10 to the minus 1 inches squared. Both of those are the same. So I just wanted to give you a couple of quick problems. We're going to come back in another video and do more conversion problems and throw density in as conversion factors as well. If you haven't watched the videos on significant figures, it would be very helpful to watch them right now for the lab. You don't have to do the whole lab, but watch the video on the rules so that this will make more sense. And I'll be back in the part 3.